Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this is a collaborative work. So we have been working on this for the last 6 months or 6 to 8 months or so. And it grew out of the GrayWulf work we were doing last year. We have actually built a low power cluster. You can see some of the blades there. So I would like to start also a little bit with the big picture. So for the data intensive scalable computing, there are a bunch of very obvious trends today. So we have large data sets which are here, but we still don't have obvious solutions which are just off the shelf for the scientists that they can just plug in their code and run. And we don't have a national infrastructure. The national infrastructure is very CPU heavy. And basically all the big supercomputer centers are just today are trying to build basically more I/O capabilities into the system. Generally, the problems that we are facing are such when the data sets are too big to fit into memory, so we can't use any of the caching and so on. And basically we need sequential I/O. One can argue why sequential I/O, because once we have a petabyte, then and we have to use random I/O, then basically we better work on cosmological problems, because it will take the age of the universe to finish it. So the only hope to tackle these problems is to at least use as sequential I/O patterns as we can. And even the high-performance projects today are starting to choke on I/O. So basically the largest hydro simulations or cosmological simulations, as I will show, they are limited essentially by disk space and I/O bandwidths rather than actually the science needs. So scientists would like to run much bigger simulations if they can. There is also an emerging sociological trend. Data collection is done in ever larger collaborations like the virtual observatories. So you can think of the Sloan Digital Sky Survey, LSST, or NEON, or the oceanography projects. So basically, these focus and collect the data, and then they archive the data, and most of the analysis decoupled from. So this is a disruptive change in science. So basically, science will be done on the archive data sets in much smaller groups. Typical data sets that are challenging today are now reaching the 100 terabyte range. They were in the tens of terabytes a year or so ago, and today they are hitting the 100 terabyte range. And in a very shortly, so probably in about a year, we are going to hit the petabyte scale. That we consider difficult and challenging. So basically, we need to build petascale database facilities and that are also easy to use. Scientists are cheap, so we will never buy EMC systems. And so typically, if we have a budget, we would like to maximize the amount of funds, so we like to build our own from cheap off-the-shelf components. So interesting to see that a very similar vacuum led to the emergence of the GrayWulf in computing about 10 years ago, where the traditional supercomputer system just didn't do the job that scientists wanted to use, and the same attitude led to, so once Tom Sterling produced a recipe that build your own, people embraced the GrayWulf idea very widely. But how can we classify what is data intensive and what is not? So I would like to go back to Amdahl's laws, sort of due to a paper that we wrote still with Jim. And in particular, one of Amdahl's laws that Amdahl said that one bit of sequential I/O per sec is needed to keep a CPU happy at the one instruction per sec level. So basically, a system is Amdahl balanced if we have 1 bit of I/O per instructions. And so one can compute this ratio. So I did this, or we did this in this paper. And this is basically the Amdahl number for a bunch of different systems. So for a typical GrayWulf cluster, it's about 0.08. So for a power desktop that people can put a bunch of disks in it, it can be as high as 0.2. Then again, for the Amazon, this is the Cloud VM is the Amazon Cloud. So there was a paper which was trying to read from Amazon S3 on multiple stripes. And basically, they could get about 20 megabytes per sec in the Amazon virtual machine. SC1 is deliver more, and I think SC2 were numbers given to me by Ralph. And of course, these are all dependent on how many I/O nodes you stick on the machines, but these are really typical for today's supercomputers, and I think Pittsburgh is actually way ahead of the pack. So this is a system that we built at Hopkins that we call the GrayWulf. It has Amdahl number of 0.5, and I know of one system that is commercially used, that is the eBay system that has an Amdahl number of 0.86. So, but they have 120 disk drives per server, and these are all 15,000 RPM drives. So they have a different order of magnitude, many orders of different magnitude budgets than we do. So, but what is nice about the Amdahl number that you can also compute it for data sets. So these are some of the simulations. So the Aquarius is a cosmology simulation done in Munich. So you can take the size of the data and the number of CPU cycles that was required to compute it. Okay, and Aquarius was done in Munich. Via Lactea was done by Piero Maddo at Oak Ridge. And this is a friend of mine did a material science simulation on the TeraGrid. And so typically, the color codes that these are then the Amdahl numbers of the typical supercomputer hardwares on which these simulations were run. These these data sets were processed and ran on a GrayWulf. That's the green arrow here. So that's what the hardware can produce. And these are the data sets that were generated. And these are different logs. So this was based on the query logs from the Sloan Digital Sky Survey database machines. So we can see that on the database machines, we pretty much saturated the hardware. And on the other machines, as we went a little bit away, so there is an increasing gap, basically, between. So as we go to higher and higher end system, the gap between the hardware and even the actual data sets is growing bigger and bigger. And it's interesting to understand why. Once we look at the data set sizes in each of those simulations, and basically everybody is today stuck between 10 and 100 terabytes. So these simulations could actually they would be happy to output and utilize more of the I/O bandwidth on the supercomputers if there was more scratch space than 20 or 30 terabytes. But in Oak Ridge, they couldn't get. So with Piero, we are currently working on the next simulation where he would do 20 terabytes at the time, then we transfer it to Hopkins, then we do another 20 terabytes, and we would build up essentially a 500 terabyte data set for a next generation cosmological simulation. There is only one petabyte data set is Penn-STARRS, and actually this is still not there. In a year it will be there. So it's already kind of putting out, the system is already putting out data, but it's not producing yet. And you can see even everything else, so the Sloan queries, when I add it all up, it's sort of between 10 and 100 terabytes. So how can we build, in a practical terms today, using cheap components, how can we build a scalable and data-intensive architecture? So I'm not talking about the $200 million range, but something that a university group can afford. So this is a project that we really started out with Jim. So we were on this path for many years. And so we decided to, I think Dan Fay came up with the name GrayWulf, combining the GrayWulf idea with Jim's name. So this is a cluster, GrayWulf-like cluster of database nodes, which are very disk heavy and I/O heavy. And we are exactly using locally attached disks, so exactly the way we heard in the previous talk. So the goal was to build a machine with a very high Amdahl number, using modular commodity components. So we have 50 servers, roughly 1 petabyte of disks, 500 CPU, and the DDR InfiniBand. We have a 10 gigabit lambda uplink to UIC, so we can move data in and out. And we have been implementing various reference projects. And funding came from mostly from the Moore Foundation, Microsoft, and Penn-STARRS. But, so first of all, we built a 200 terabyte database from the Sloan, and the demo of this demo won the storage challenge in last year's supercomputing. So what we were able to show that the aggregate I/O scaled to over 70 gigabytes per second on this system. So 1.5 gigabytes per second per node. But when we run database queries, they came close to the speed of light. So they became within 72% of the raw I/O speed of the subsystem using SQL Server. It was very cost efficient. So 1 gigabyte per second bandwidth cost us about $10,000, which is much better. NetEase sells a system that they can do similar I/O speeds, but at $1 million for 10 terabytes. So the Amdahl number is 0.56, but basically we were hitting the power wall. So we built the system, put it into the physics lab that was converted to a computer room, and then essentially we ran out of power. And so right now the building is undergoing a reconstruction. We are bringing in new transformers to hook up yet another lab so that we can add another petabyte next year. But after that, we will run out of the juice that's coming into the building. So we were already building with Andreas little wireless modes that measure with clamp-on meters that can measure the power in each circuit in the room so that we can actually understand the time, the temporal dependence of our workload, and maybe we can do some fancy power management and so on. We also have hundreds of Microsoft-built temperature sensors in the computer room. And anyway, so the power is becoming the main concern. So how can we do better? And along came solid-state disks. So around Christmas time, the prices started to come down to the acceptable ranges. And the new solid-state disk, basically OCZ and Intel, can perform a 250 megabyte sequential read, 200 megabytes per second sequential write, and 1 to 2 watt power. So that is very attractive. And even now you can write them enough times that essentially their lifetime is less of a concern. So how have been people trying to use these solid-state disks? So there are several companies which are trying to put SSDs or flash memory into existing high-end servers. So there are a bunch of PCI-based cards where you put in, so the Fusion I/O and OCZ is building those that can do 800 megabytes a second. But basically, even if we put like 3 of these disk drives on an existing high-end RAID card, it saturates the RAID card at that point. So, and then shortly after, if we can start putting more cards into the PCI slots, then we saturate the PCI bandwidths. And so then we have to add another expensive server to this. So we have decided to take an orthogonal approach, or the opposite approach, so scale down. Again, back to Jim's ideas, build the bricks, the Cyberbricks that Jim talked about more than 15 years ago. So that take an Amdahl blade. So Amdahl blade is basically 1 SSD per core. Try to take advantage of some of these very low power motherboards. And it turns out when we do this, when we look at these, basically, so the OCZ Vertex is a typical drive, so 120 gigabytes, 250 megabytes a second, 10,000 IOPS, and roughly 300. It was actually $300 in March. Now it is about 400. So the trend is such that there is now suddenly such an exploding demand for SSDs that there is a premium on them. So in order, when we are preparing now for supercomputing, we had trouble. We had to go like 5 different web stores to buy 10 drives here, 10 drives there, simply because it was out of stock everywhere. Anyway, low power motherboards. So there are some motherboards. I will show a little bit more about this. But you can get today motherboards which are dual cores at 1.6 gigahertz at 28 watts or so. And the combination, if we just do the rough numbers, 200 megabytes per second, it's 1.6 gigabits per second when we combined it with a 1.6 gigahertz. So basically, it's an Amdahl number of 1. So we looked at a whole bunch of different boxes. So we looked at an Asus, for example, an Asus E box. That is a $300 box. You can buy it off Amazon. So that has a single atom core in it. Then Intel has a dual-core board. Zotac has the board with the Ion chipset. Axiom Tech has a Pico motherboard, which is really tiny. And it uses an Intel chipset, which is supposed to take only 5 watts. It actually takes 15. And then there was the ALIX experiments here at CMU, which are using as an AMD LX800. So a whole variety of different CPUs and configurations. And these are some of the quantities. First of all, a bunch of columns. So this is the CPU speed aggregated over the number of cores times the clock cycle. So I didn't count flops or anything, did something very simple. This is the memory in gigabytes. This is sequential I/O using two. So all these systems use two solid-state disks, and the Alex was using just a flash card. This is the random I/O in IOPS, in thousands of IOPS. This is the total amount of disk space in terabytes. This is the power in watts. And this is the cost. The cost includes the hardware. Then I called up Hopkins Physical Plant and asked them, what do we pay for a kilowatt hour? So for us, it is actually 15 cents per kilowatt hour in Baltimore. And then we multiply it by 1.6. We took this from James Hamilton's papers. So for the AC overhead. And the price assumes that a 250 gigabyte SSD by this fall would have been $400. It didn't happen because of the scarcity issue. So that's a little bit optimistic, but that only affects this capacity column. We can still buy a 120 gig OCZ for less than 400. So basically, we can get, it doesn't impact the I/O speed because that's the same for the drives of the different capacity. So we can get 1 gigabyte per second sequential I/O for 2400. So already today it's a factor of 4 better than on the GrayWulf. Scaling. So this is actually, so we tried to take then this chart and scaled it to a couple of, where we kept one of the factors constant and for comparison. So let me just look through it very quickly. So the first column was to fixed price. So at a constant price. So for the price, and always compared to the GrayWulf. So that's our fiducial node. So let's see. So the total ownership of a GrayWulf node is $19,000. This says that how many nodes of a particular kind cost the same amount. So for the price of one GrayWulf node, we could buy 16 of the Zotac, for example. And then for the 16 nodes, the aggregate sequential I/O performance would be 8 gigabytes per second compared to 1.5. At a power of 400 or 500 watts against 1150. But what is more interesting is the constant sequential I/O. So how many of these little boards do I need to beat basically the big server? The number is 3. And so at a cost of roughly $3,500 or so, I can build a system that has 1.5 gigabytes per second and at 90 watts power consumption. And what is also interesting that there is a sweet spot. Actually, this arrow should have come down here. There is a sweet spot. No, it's at the right place. Sorry. So basically, in the sequential I/O, when I go this ASUS and the the ASUS motherboard is a single core Atom, and that doesn't perform anywhere as well as a dual core. So just a single Atom is not good enough, essentially, to handle the the I/O, and then when we scale down farther, then the performance is dropping very rapidly. So there is a sweet spot, basically. The dual core Atom is today the sweet spot. And this will, of course, change with subsequent generations of
What's hybrid?
Oh, hybrid is that we take, some of the motherboards have 3 or 4 SATA ports. So that I started mixing essentially two OCZ drives and a bunch of Samsungs, which are still low power regular hard disk. So, and then we can also add capacity at a moderate increase of power. So we mix essentially those two. So scaling, let me go back. Scaling to constant power. If I scale to constant power, so then essentially, for the same power, I can buy 38 of the Zotac, of the Atom boards, basically need as much power as a single GrayWulf. And then at that point, I have something like a factor of 15 higher sequential I/O speed. So this is, I think, probably for deployment, for data-intensive or I/O-intensive performance, this is kind of an interesting number, that if I'm power constrained going this way, I can basically increase my I/O capabilities by a factor of 15 or 16 today, on today's prices. And the constant disk size is where we are suffering. Essentially, in order to match the I/O capacity of the GrayWulf today, we would need 45 nodes, and that would be pretty expensive. So this would be like $53,000 versus 20, although the difference is much less. So it's only a factor of 4 today. And so there's an interesting number, then I run the spreadsheet, that how expensive would a 750 gigabyte hard disk be that to be cheaper to essentially beat this hard disks even on this scale. It turns out at 400, as soon as the SSDs cross over this limit, it will be cheaper to build these SSD-based systems. And this can't be too far out, basically, maybe a year. So status. So we compared all these motherboards. We are building a 50-node cluster that should cost less than 50K. It helped that we got a whole bunch of motherboards from NVIDIA, but I will still include it in the price. So with 2 OCZ Vertex drive, we can definitely get 500 megabytes per second sequential read, 400 megabytes a second sequential write, and 20,000 IOPS at 30 watts. So there's the bottom line. But the Ion chipset that NVIDIA built, they built it for the Apple TV box. So it has a bunch of GPUs on it so that they can do high-definition TV on this, which the Atom couldn't do it itself. So it's also the only low-power motherboard that can run on 4 gigabytes of memory. And in principle, the Ion chipset has 40 memory pins, so it can run a whole bigger memory. It has 4 SATA, so 3 regular SATA and 1 eSATA, 1 external SATA. And it has 16 of the stream processors. So the motherboard runs around 28 to 30 watts. But what is particularly attractive about this is that since the Ion chip itself is also the memory controller for the whole system, it has a unified memory space. Okay, so the Atom sits in the same memory space as the GPU. We don't have to copy through the PCI bus the data in. So this is quite beautiful. And CUDA now supports something. So the whole CUDA API has a secondary calling the zero copy option that instead of passing the data to a texture map, I can provide a pointer. So I don't have to copy. So this is something really nice. Yeah. No, so there's a single chip that contains all the normal Intel chipset functionality plus 16 GPUs. So the standard chipset does basically a memory controller, I/O control, PCI bus, sound card, video output, and NVIDIA also shoved in basically 16 GPU cores. Okay, and made it run also still at a low power. And so the beauty of this, that this is, so you need only these 2 chips to build a motherboard. And NVIDIA already demoed also a Pico motherboard that is the same size as a laptop disk drive, so 10 by 7.5 centimeters. That's really remarkable. Yeah.
2 slides ago, you mentioned that the speeds of the writes are about 500 megabytes per second?
Yeah. So basically, we max out the motherboard with 2 SSDs. When we add the third one, then essentially the Atom starts to choke. We basically just use the built-in gigabit Ethernet.
So you would never be able to saturate 500?
But that's not actually. So the typical eScience applications are typically scanning through lots of data, and if we can run the first pass of the science analysis code right as we read the data of the disk, at that stage we can then decimate or even, so roughly 10 to 1% survives, hopefully, the first pass. And then we are in the right ballpark with the gigabit. And then again, the aggregate network bandwidth is then 50 gigabits per second across the cluster still. Okay, so where are we? Yeah, so we are playing with, so one row on this shelf that we are building will be different disk configurations so we can compare. The 2 candidates that we are playing with Samsung drives, which are 1 terabyte, 128 megabytes per second, but 7200 RPM, but at 7.5 watt, and the laptop version of this, which take only 2.5 watts for 500 gigabytes. And so the projections that we can really, it's basically the motherboards which will max out the system. So we are running low-level benchmarks right now. playing with scalability. We are comparing various real-life applications, so we are trying to run CUDA from SQL Server. And that was actually pretty tricky. So as we learned the hard way, first of all, if I have probably 2 minutes. So one problem was first we plugged in the board, and then CUDA didn't come up because we didn't have a display plugged in. So we had to trick Windows. Windows installed, if it didn't see a display plugged in, it believed that it installed a virtual display driver. So we had to build a little plug with 3 75 ohm resistors on the RGB outputs. So that was one. Then we turned on remote desktop so that we can access the cluster remotely. Okay, CUDA went away. So it turned out that, again, if you RD desktop in, then Windows installs again a virtual display driver. But luckily, VNC, on the other hand, does a screen capture on the hardware card, so we are running now VNC. And then finally, we luckily wrote a script that installed Windows 7 on all the machines. And then essentially, SQL Server and CUDA crashed. So they tried to install in the same service slot. So it turns out that we can do this on XP, so we are now back to XP4 now until NVIDIA is kind of patching up the CUDA framework. But basically, so it was hardwired both into SQL Server and into CUDA to use the same service slot in Vista and later. So it was, but we got it working. So the idea is to take 300 million galaxies from Sloan and compute photometric redshift, which is running a random forest regression tree analysis, so computing 50 regression trees per object. And typically this takes a week on a reasonable size cluster. Today, we think that we can, using this combination, we can actually do it in about 20 minutes on this cluster, just to demonstrate that we can do real-life problems. Summary, science community is starving for storage and I/O. We need some objective metrics for these systems to clearly separate from the CPU-intensive architectures, and also this can be used to characterize our computational problems, that what problems are adequate for what architectures. Current architectures cannot sail much farther, primarily because of the power issue. So we cannot just buy more disks and more servers, because, at least at universities, we cannot. So Google can afford to do it, Microsoft can afford to do it, Hopkins cannot. So the future is in low power and fault-tolerant architectures, very much along the line of Randy and Garth's talks. And this represents the whole novel sets of system challenges. If I wanted to capture this in sound bites, so basically yesterday, high-end computing was about CPU cycles. So today it is really about data access. And tomorrow it will be entirely about low power. Thank you very much.
When you multiply the number of nodes out, a lot more nodes, each one with lower power, like join, it's going to get more expensive out of that.
Well, it depends on how you partition your data. So the magic is in the partition, and of course, Microsoft with the data Allegro acquisition is going that way, so to have a massively scaled out SQL server. But yeah.
Right, if all else being equal, if I increase the number of nodes, there's more communication that has to happen between.
Yeah. But again, I think as we scale down and out, I think we can use cheaper network adapters, because if I shove a lot of bandwidth into a high-end server, then I also have to increase my network bandwidth proportionately, but that gets disproportionately more expensive. If I go to a quad-speed InfiniBand, and I have also been to InfiniBand driver hell, so that's another not a good place to be. So.
Any other questions? And let me open up to questions for any of the three speakers. Well, if not, then, go ahead.
So you showed a limitation on the SSS queries at about the hardware rate. Do you think people are limiting their questions because they can't do that?
Yeah. So for example, okay, so one,
the demand is much higher.
yeah. So for example, one classic example was last year the problem I think for supercomputing, the real life problem to demonstrate on the power of the cluster was a real life query that was running for 13 days at Fermilab in the Sloan archive. And it was a multi-stage workflow, but it essentially maxed out the whole systems in the 13 days from beginning to end. On the cluster, we were able to run it in 12 minutes. So obviously, people would want to use a 12-minute solution if they can.
Well, and then they'd ask for more.
And then they would ask for more. Yeah.
I'll ask one more, I guess. Do you envision, before actually bringing those three speakers, do you envision architectures that are sort of specially tailored to a particular kind of application? So rather than saying sort of broadly eScience application, something even more narrow than that?
I think we will see more heterogeneity in the architecture than we see now, but if we wanted to leverage commodity components, we cannot go way too much. Okay, so one technology is indeed the emerging NVIDIA, so GPU computing. That's obviously going to here to stay. I think it needs to be done at a lower power. And as I understand, NVIDIA is working very hard to actually scale down, and who knows what happens when Laravel comes out. So that is here to stay, definitely. I think solid-state disks are probably going to be here for probably 5 to 10 years until the next set of physical devices coming, which supersede basically flash with better physical properties, and then they go out the door. And I think kind of hard tapes are out. So obviously, and hard disks are probably here for the next few years until also we have run with SSDs long enough that we see their failure modes over time.
I think that unfortunately there's lots of people who buy capacity rather than performance.
Yeah.
And more people buy capacity than performance. So
Yeah.
while this the designing for performance, as Amdahl encourages us to do, is the right thing for some applications, the bulk of the systems will still be about capacity. One speculation that I've begun to see is that we'll see big high-end systems that are essentially two clusters, where the second cluster is the storage subsystem for the first cluster, and the first cluster is the bigger one, compute-oriented, and you do data analytics in the second cluster close to the data.
Yeah, and I should have mentioned that Hopkins in the same room on the same InfiniBand switch, we have a 2000 CPU GrayWulf cluster, which we can basically do peer-to-peer to any of the database nodes. So yeah, I fully agree.
Okay, so I think we can have a 10-minute break and for the eOcean presentation and the rest of the recording. So let's thank all three speakers again.